Okay, first, I want to thank to the organizer for the opportunity of giving a talk. I hope next year to be with you in person, attending this night meeting. So I will talk about this work that is mainly from my PhD work that I did with at INAOE in Mexico, under supervision of Dr. Omar López Cruz and Dr. Christopher Añorbe at INAOE. So currently I'm working at IAC. I am doing a postdoctoral position at Instituto de Astrofísica Canarias. So, okay, the objectives of this work was mainly to perform a photometric study of nearby galaxies. We use the 2MASS data in the near infrared bands, the 3 bands of 2MASS, in order to estimate the structural parameters of galaxies. And we focus on the scaling relation among the global properties such as luminosity, size, and kinematics, and also those ones involving the black hole scaling relation with the host galaxy properties. Here in the bottom plot, I show you the distribution of our sample. We have a sample of 101 galaxies. In the left panel is according the Hubble type. We cover from early type galaxies, including elliptical and lenticular, to spiral barred galaxies. In the middle panel is the distribution according to the KS magnitude from 2MASS. We have galaxies brighter than magnitude 10, and in the right panel is the distribution according to the redshift. We have galaxies with redshift below 0.1, and we know near infrared wavelengths offer the advantage that they are less affected by galactic extinction, and also that these wavelengths are more sensitive or are a good tracer of the older stellar population of galaxies. So we perform our two-dimensional photometric study using GALFIT. GALFIT is an algorithm that allows you to model the surface brightness distribution of astronomical sources. And you can use analytical functions just as the Cersig profile, exponential disk profile, for instance. Here I show you the Cersig profile by José Luis Cersig, of course. And this is a parameterization of the surface brightness at the effective radius, which encloses the half of the light. And here the parameter n is called the Cersig index. Here I show you the Cersig profile for different values of Cersig index. And for small values of Cersig index, the inner profile is shallower, while for instance, for large values of the Cersig index, the profile is steeper. And also, okay, there is some difference at the outer region, depending on the Cersig index value. Regarding the model selection that we did with GALFIT, briefly, we start by fitting a Cersig profile, regardless of the galaxy morphology. For instance, if we have a disk galaxy, we fit individually a Cersig component for the bulge, and also exponential disk for the disk of the galaxy. We fit this individually, and then if we have 2 or 3 components, depending on the morphology, we feed finally the components together in order to try to obtain the final model. In this image is illustrate this procedure. From top to bottom, we have 3 different galaxies of our sample. From left to right, we have in the first column the galaxy image. In the second column, the model generated with GALFIT. In the third one, the residual image given by GALFIT. And in the last column, we have the surface brightness profile for each galaxy. And this 1D profile were generated with Ellipset. That is a code developed by by our research group. If you're interested, you can use it. It's a public and free code. Here is the web page. And also, as a part of one of the results is here that we also find this sky over subtraction issue related to the 2MASS data. This also was pointed out by Schomburg in 2011, but here in our work, we add that this over subtraction on 2MASS data is mainly for early type galaxies. In this image, we have 3 different galaxies per column. The first 2 columns are for early type galaxies, and here the red and blue lines indicate 2 different data sets from 2MASS both. But for instance, the red one is for the large galaxy atlas. In the large galaxy atlas, the sky was subtracted, while in the blue line is for the archival data from 2MASS with the sky. So we see that for early type galaxies, this effect is present That's why in the first two columns we see there is no this mismatch or this discrepancy between the two profiles. While for a late-up galaxy in the third column, in the right column, for instance, a spiral galaxy, we see that both profiles match very well. Also, in this work, we focus on study the bulge population. We can classify bulge mainly in two categories, as classical and pseudobulge. Classical bulge, they have similar property as elliptical galaxies because it's thought that they are formed in a similar way as elliptical galaxy via major measures. Also, while pseudobulges, they share properties as the disk of galaxy. So is thought that they are formed via secular processes in a continually and slowly way. So in this plot, I show you the three criteria that we use in order to try a robust classification of bulge. In the left plot above is the Cordoba relation between surface brightness in the vertical axis with the effective radius in the horizontal axis. So those stars get falling as an outlier of this relation can be considered as pseudobulge. In the right plot above is the Sersic index distribution. The red one histogram is for classical bulge, while the blue one is for pseudobulge. So regarding to the Sersic index, is taken the Sersic index greater than 2 as a threshold. So those targets with a Sersic index greater than 2 will be considered as classicals. And in the bottom plot is another criteria using the velocity expression of galaxy. Here the limit is sigma greater than 150 km per second are for classical bulge. That is the red histogram, and the blue one also for pseudobulge. Regarding the scaling relation that we constructed in this study, this one reason why these relations are important is because any theoretical model of galaxy formation and evolution must reproduce this empirical relation. So here I show you, for instance, the relation between the black hole mass in the vertical axis against the velocity dispersion sigma in the horizontal axis. So, for instance, this relation implies that there is a coevolution between the supermassive black hole with the host galaxy. So, okay, here I show you some of the results. In the top plot is the Cordoba relation that we constructed with our data using this TUMA data. The blue dots are for pseudobulge and the red ones for classical bulge. And here, using the three criteria, in order to get the final classification, the target should follow at least 2 out of the 3 criteria that I mentioned above. So about the 40% of the sample is classified as pseudobulge. Here in this Cordoba relation, we see that most of the pseudobulge follow as an outlier of the relation. Below is shown the fundamental plane that we construct for our sample. Here are the 3 bands of TUMAs, J, H, and KS. So we see here that also we, yes? Okay. Okay, yes. There is also the distinction between these two populations is not so clear as in the Cordoba relation and also as in Faber-Jackson, that are the projection of the fundamental plane. Okay, here also the color magnitude relation that we did, and here we highlight that the color magnitude relation can be used as a classificator for a luminosity or absolute magnitude of -22. That is a vertical dotted line that is indicated in the 3 plots. Regarding the black hole scaling law, here I show you the connection or the relation, between black hole mass in the vertical axis with the luminosity of the bulge in the left side, and with the sigma, the velocity dispersion, in the right side. So here, besides that, we're in agreement in the sense that the sigma relation is the one with the lowest scatter. Here we want to highlight that pseudobulge populate the lower part of the relations. The pseudobulge are the blue dots. And also that most of the pseudobulge here are following the relation. That is something unexpected. This also has been reported in the literature. But also we want to, before claiming that this trend is completely true, we want to extend this study in more detail because we have a limited sample, for instance, talking about pseudobulge. Okay, and finally, okay, here I show you some other relations that we construct. In the bottom part is the relation with the black hole mass in the vertical axis with the Cercic index. This is the weakest relation that we obtain, and also it has the largest scatter regarding to the others. And this is interesting because some works point out that the relation between the mass of the black hole with the Cercic index could be as tight as the one with the luminosity of the sigma So, but with our result, we rule out that possibility. And just to finish, also our PhD student at Inaue Fitsum is, well, Regina is carrying out right now a study in Galaxy cluster. He's focused in this moment in the Coma cluster in order to see the effect of the cluster environment on the galaxy morphology, also and to put this result in the context of bulge and pseudobulge. And also we want to see the story formation history of the galaxies in Coma cluster. We already submitted a Megara proposal. And just to finish, now, finally, I would like to mention very quickly, right now I'm working on CHARC's project. This is CHARC stands for Southern Asia region of the K-band survey. This is a survey performed with the VISTA telescope, and this covers 300 square degrees. This is the coverage, that is the red squares. Now this survey is in the K-band, and we already made the data release 1 in last January. So if you're interested, please let us know. This is a survey that has deep, almost magnitude 23 in the K-band, and is covering mainly this field, the subgalactic pole, and also the gamma 12, the gamma 15 fields. So if you're interested, please let me know. You can contact me, or also to Helmut and Barwer, who is the PI at IAC. So, and here is the summary, and that's it. Thank you for your attention.
Okay, let's thank to Emmanuel. We have a time for a very brief question. Virginia Cuomo, yes?
Yes. Can you hear me?
Yes.
Yeah. So I have a question. Thank you for your presentation. About in one of your first slides, you showed some of your model coming from the photometric decomposition. And in one of the galaxy, I see that one galaxy is in interaction with a smaller companion. So I was wondering, how can you treat the light of the companion in your photometric decomposition?
Okay, yes. In this case, I did the both fits by fitting first the two galaxies individually, and then I fit them both together. So in this case, I found that the final model was better if I consider only the here M51A galaxy, so the largest one. So that's why here in this image I put the residual image. So I found this for this model for this galaxy that it was better by taking individually both galaxies. I don't know if this answers your question.
Yes. Okay. Thank you.
Yes. Thanks.
Okay. Well, let's thank again to Emmanuel. If you have more questions, you can ask him in the Discord channel.
Okay. Thank you.